And now we're in chapter 3, and the first part will be going into what we call modular representation. Basically, we have a group, you have a vector space, and combining relationship within the vector space and the group, we're able to get what we call a G module. And we're using the concept of modules and trying to see how we can represent them in matrix. So matrix representation of modules is what we're doing here. So it's called modular representation. And so like I was saying, we have a vector space. So we begin with what we call automorphisms of vector space. So we say let V be a vector space over a scalar field K. An isomorphism of V onto itself is an automorphism of V over K. So we need to know the definition of an automorphism of a vector space. So there are things to note, and for me the key thing I want you to note is this, what we call the set of all automorphisms of K form a group, and we denoted this. And in short form, when we don't really worry much about the field, we just choice of the field, we just write it simply this way. You can pause the screen and read every other information that is given on the screen. Okay. The next thing you need to know is what we call automorphism representations of a group G. So any homomorphism, I'm sure you know what homomorphism is. Okay. From G into the set, remember what it is, it's also a group set. So the set of automorphism over K forms a group, and we denoted it this way, recall. So this any homomorphism from G into the set is called an automorphism representation of G. So we have something called an automorphism representation of G, where V is a suitable vector space over the scalar field K. Okay, so there's something we should note here, and that's the relationship between elements in the module when regards as an automorphism. Okay, so we can relate it this way. There's something we also need you to know, and that's what we call the G module itself. So now we know what an automorphism is. There's a function that combines these elements together, right? Working with our vector space within the group G. You can see here we have a vector space over a scalar field. An isomorphism of V onto itself is called an automorphism. In a collection of such, we get which forms a group, and we have a notation for it. And now we just define homomorphism, okay, which has to do with the mapping from G into this group. So we happen to have a group, and that homomorphism brings a relationship between the group G and the set of all isomorphisms of the vector space V. With the rule, if you happen to have this map from V to V, you have this relationship. So now we need to know what the G module is. So we have a group G, and you have a vector space over the field K, and it is called a G module on the grounds that if you pick an element from G and an element from the vector space, that is V from the vector space, X from the group, the Vx will satisfy some conditions, and these conditions are Vx will lie in the vector space V, and this distribution, the multiplication of HV plus KW and multiplied with the sum over X will give you this as a distribution with all these elements. One is from, this is capital H, not small letter H. So something's missing here. It's from V, capital V. These terms are from V, while the others are from K. That's V, and W, letter W are from letter V. That was missing in the typo. Okay, and we also have that Vx equals to Vx. That's associativity is kind of like for the multiplication, and that identity is if you take the vector space times 1, it gives you back the vector itself, not vector space, but the element in the vector. So these four identities, once satisfied by the product of these two elements, it makes the group G and the vector space over K to be called a G module. Okay. Next is what we call a submodule. So if you have V and it's a G module, now you know what a G module is over K. We say that U is a submodule module of V. If U is also a vector space over K and it is contained in V, and second condition is that U is a G module. That is, you can pick U from the vector space U and X from the group G, and this product will remain in U. Also satisfying all the other properties of the G module. Note carefully, this is lettering went wrong while the slide was being made. Okay, now the next definition you need to know is what we call the reducible and irreducible G module. So a G module is reducible over K if it possesses a proper submodule. So if it possesses a let me take it again. Now a G module is reducible if it possesses a proper submodule. So there's a proper submodule, it means you can reduce it. Otherwise, it is said to be irreducible. So if I happen to find a proper submodule, say U in G, it means that my G module, in V is my G module, right? And use my submodule and it's proper, then we'll say that my G module V is what? Is reducible. However, if it is not proper, we say that it is what? Irreducible. That is the vector space, or the G module V is irreducible. Okay? The next definition you need to know is what we call composition series. The submodule, so now you know what submodules are. Submodules are also modules, right? And they satisfy the conditions of a G module, right? There. Okay, so we have submodules U1 to UK that they are said to form a composition series if the chain of submodules, so you have a chain here, see how it is represented, if this chain holds. So once you have this chain, we say we have a composition is formed by the submodules U1, U2 all the way to UK. Sorry, that would be U not what, well, U not the same as 0, so it still makes sense. Okay, now the next definition is 3.9. It says complete reducibility of G module. So if you are told to define the complete reducibility of a G module, you simply say the G module V over field K is said to be completely reducible, so you can break it completely if this sum exists. Can you see the direct sum of the UIs? Okay, that is this G module is same as the direct sum of the UIs are irreducible G modules over K, where the UIs are irreducible. This is capital U, not small u. Okay, capital UIs are irreducible G modules over K. You know what irreducible is right now, I'm sure, because we have defined all of those terms earlier. Okay, so once we have this, we say it is completely reducible if this sum exists, the direct sum exists. Okay, so now we go into the theorem. We have a theorem in your lecture notes. It's 3.6. It says you have a G module V and its dimension is M, and that it possesses a submodule U of dimension R. Remember that the V module is also a vector space, right? And the U, also submodule, is also a vector space. And this one has V has dimension M, while U has a dimension of R. We want to show that this equivalent matrix Bx, also an equivalent representation which we have shown earlier in chapter 1, that this matrix is same as this, where T is any non-singular matrix with coefficients in K, and the AX is taken from the general linear group of K, an M by M matrix, and C is an R by R matrix, DX is an S by S matrix, and EX is an S by R matrix. And the sum of S and R will give us the sum of to give us M, which is the dimension of the representation matrix AX. So we want to show that once you have this G module with this property, with a submodule, that you would get this particular representation. So let's see if that's possible. So first, we know that this is a representation. So a group G definitely will have a representation. So we let AX be the representation, and afforded by V. Remember, we're talking about a G model, so it's definitely linked to our AX, which is a matrix representation of G. Okay, so we now refer V to new basis, which is adopted by the subspace U. How do we mean now? Definitely we know that V has a subspace, a submodule U, right? And it definitely would have its own basis because they're all vector spaces. So now, first we choose arbitrary basis because we don't know the exact basis, so we can choose the basis for U, and these are the bases, U1 all the way to UR. We choose basis for them, and then this can be extended to the basis of V by using a suitable vectors, which is the all the way to WS. We're able to stop at S because we know that the dimension of V, the vector space V, is M. So we stopped at S so that by the time you add S plus R, you get the sum M, because we're extending this basis to those of the bases of V. So basically we're just adding more bases to those of U so that we can get all the bases together for V. It can't exceed those of V. So we have assumed this based on the knowledge of the dimension of our G module V. Okay, so that means we now know what the basis of V will look like, right? So V has a basis of the form, this one you see here. We've labeled it asterisk. So in this new basis asterisk, we can form this matrix here. How can we see that? Well, if we let X, because we want, if you notice how the matrix looks, there's X in our matrix there, right? So we let X act on our basis. So we let X act on the vectors of asterisk. So these are vectors, right? The basis, so we let X act on them. So more like X. So let's see, I have typed it here, right? Good. So since U itself is a G model, so when X acts on it, like that's for the UI. So for the WIs, it will just have W with the X right at the side. Okay. So now we know that U itself is a G module, right? Because it's a submodule. So if it's a submodule, it means that if I pick an element from U and an element from the group G itself, it will satisfy this condition, right? Thus, we can form an equation. And this equation will look something like this, with the Cij's from K, right? See what we've done there. So we can form that. And then and note, we're summing from I to R. Why? Because we're working with the UIs, right? Okay. So for the W, remember we just choose them arbitrarily. We can't really say anything much other than the fact that they are coming from the vector space V, whose dimension we know to be M, right? Okay, so with that said, so okay, yeah, we can only state that it is, so we can only say that it is a vector in V, and so we can express it as this. You know why I could do that? Because I know what I'm targeting, but then I'm careful to note the sum, the first R of them and the first S of them for the W's, right? So there's a mistake here. So this sum goes all the way to R, and then it goes all the way to W because of the relationship we have here, right? So that's the sum here, and that's the sum here when we've taken all the values of in terms of WH. So this is WH here, not U. Okay, that's a mistake, a typo. So when we know what the E's and the D's are, they are taken from field K, okay, because that's where we are running our sums through. Okay, with that said, so we now know what Ux will look like and what Wx will look like, noting that the sum runs from I to R and the other one sums from J to S, because when you sum I plus S, it will give us a total sum of M vectors in V. So with that, let me go back, because we're going to now look at them. So if you write them in form of matrices, you see that this terms will form a block. Let me clean this so that it's legible. So if you want to write them in matrices, like 100 level math, this will form a block, and this will form a block of matrix, and this will form another block of matrices, right? So if that is the case, see what happens. So we have this is now representing the block of matrix with the C's, the ones with the E's, the ones with the D. The question is, where did we get 0 here? Let's look back. You can see this is 0 because there's no other term after this. It stops at R. It doesn't go all the way to S here. So there's no term plus something all the way to S for the UIs, right? So with that, you can see that we've gotten what we were seeking from our basis. So, and we can see that this is exactly what we want as Tx. T inverse. Let me look at it. So we've gotten what we were wanting as T inverse EXT. That's our BX earlier. Okay, and that's all to the proof. Okay, so you can rewind and go through the video again. If you have questions, you can ask in the group chat if there are any issues, or refer to your notes as we have seen in class. Thank you.